A particle moves along a line so that its velocity at time t is represented by the function v of t equals t squared minus t minus 6 in meters per second. So we are asked to first find the displacement of the particle from 1 to 4 seconds. Let's start there. So remember, displacement is going to be just the integral of the velocity function, because that's going to compute essentially the net signed area. So if we integrate from 1 to 4 of t squared minus t minus 6 dt, this will give us the displacement. So regarding how much work I'd like you to show, I do want you to go ahead and show me the antiderivative, but then I'm okay with you using your calculator to substitute in 4 and 1 and subtract the result. So the antiderivative of t to the second power should be 1/3 t to the third power. The antiderivative of negative t will be negative 1/2 t to the second power, and the antiderivative of negative 6 will be negative 6t. And then I like the notation where we have the antiderivative in brackets. We have our 1 and we have our 4, which shows that we're going to substitute in 4, substitute in 1, and subtract the results. So be sure to pause the video and actually do this computation, so it just gives you the chance to get some more practice using your graphing calculator. And we should have an answer of negative 4.5. Now let's discuss what this means. How can we have a negative answer? Or does a negative answer even make sense? Is this feasible? But remember, displacement is essentially the change in position. So we were looking at the displacement from 1 to 4 seconds. So the fact that my displacement is negative means that after 4 seconds, the particle is ending 4.5 meters to the left of where it was at t equals 1 second. Next, let's find the total distance the particle travels from 1 to 4 seconds. So total distance is going to be different than displacement, because now we want to count all of the distances traveled both to the right and to the left. We want to count all of those distances as essentially positive distance. So this means that we're not going to be integrating the velocity function, but rather the absolute value of the velocity function. So let me give myself a little more room. For part B, we will integrate from 1 to 4 the absolute value of v of t dt. Remember, by putting absolute values around the velocity function, that's essentially going to reflect the portion of the graph that is under the x-axis. It'll reflect that above the x-axis. So all of the regions will lie above the x-axis. So our velocity function was t squared minus t minus 6. We will integrate the absolute value of that function. And while we certainly could do this on the calculator, I do want to show you how we can do this by hand. So what we're going to need to do first is think graphically about our velocity function. So without the absolute values, we're just looking at t squared minus t minus 6. So we know graphically that this is going to be a parabola that opens up. And we can go ahead and actually factor this one to determine our x-intercepts, or in this case, our t-intercepts. So this is going to factor into t minus 3 times t plus 2. So therefore, we know that we have intercepts at positive 3 and at negative 2. So just thinking graphically here, if it's a parabola with an x-intercept at positive 3 and at negative 2, we have a graph that looks something like this. So therefore, when we think about doing the absolute value of this curve, so the curve I have right now is my velocity curve. That's in black. Let me try that again, make that look a little better for you. So that's v of t. So if I change this, I'll do this in red, and now we want it to be the absolute value of the velocity curve. Remember, that's going to keep these two sides of the curve the same because they already lie above the x-axis, but it's going to reflect what's below the x-axis above the x-axis. So therefore, when we integrate, and we were integrating, remember, from 1 until 4 here, now we'll end up with a region here that's above the x-axis. And then we'll have another region here. I don't have quite enough room to show all of it. So we'll end up with two regions above the x-axis. So what this tells me then is I need to use that x-intercept, which was 3, and my first region will be represented by the integral from 1 to 3, and then my second region will be represented by the integral from 3 to 4. So we're essentially going to break up this integral into two separate integrals. The first one from 1 to 3, and then the second integral will be from 3 to 4. So finding the x-intercepts really was key to breaking up this integral of an absolute value function. Now, when we look at the region that's from 1 to 3, that portion of the curve was reflected across the x-axis. So that means I really took my velocity curve and I multiplied it by a negative. So that's like a negative quantity, t squared minus t minus 6 dt. So again, where does this negative come from? That negative is from recognizing that on the original velocity curve, from the piece of the curve that was between 1 and 3, that was below the x-axis. We had to reflect that up over the x-axis. And to do that, we need that negative. But the region from 3 to 4 did not need to be reflected. So the region from 3 to 4 is just going to be t squared minus t minus 6. So this would be one way of essentially breaking up the integral from 1 to 4 of the absolute value of t squared minus t minus 6. And now, essentially, you have two individual integrals that you could compute the antiderivative of each. The negative, it's really up to you. If you want to bring this negative and have it in front of the integral, you certainly could. Of course, the alternative to that would be to distribute. If you wanted to distribute, that would be fine as well. So I'm going to just choose to bring it out in front. So there's a variety of ways of actually evaluating here. And the reason I had chosen to bring it out in front is because then the two integrals will have the same antiderivative. So we'll have that negative out in front. The antiderivative of t squared is that 1/3 t to the third power minus 1/2 t to the second minus 6t. And that will be evaluated at 3 and at 1. And then we'll have that same antiderivative, 1/3 t to the third power minus 1/2 t squared minus 6t, evaluated this time at 3 and 4. So go ahead and pause, compute this, and it looks like we are going to get an approximate answer, which I think you actually could probably convert to an exact answer if you wanted to. I'm getting approximately 10.17. And since this is total distance traveled, this would be meters. I believe our exact answer, if we're looking for the exact answer, ends up being 61/6.